is joining. Those who have joined the meeting, you all can give your attendance in the chat box. I repeat, those who have joined the meeting can give your attendance in the chat box. Let me present my screen first. Okay. Can anyone respond whether my slide is visible to you or not?
Yes, sir.
Okay, okay. So in the last class we were discussing about the stress concentration part. We yes, yes, we started our discussion with design against fluctuating load. We have discussed what is fluctuating load, what is a fluctuating stress, different mathematical models for cyclic stresses, that is that is how a fluctuating stress will look like, what is the value of sigma m, what is sigma a. Sigma a is your amplitude stress given by half times of sigma max minus sigma mean. Sigma m is your mean stress given by sigma half times of sigma max plus sigma mean, and your amplitude ratio is given by sigma a by sigma m, and the stress ratio is given by sigma mean by sigma max. We also seen what is repeated stress, reverse stress. Then we have seen that what do we mean by fatigue limit or endurance limit, what is an SN diagram, how it will look like, and this is the SN diagram for steel. After that, we also classified the SN diagram into two types. That is, one part is called low cycle fatigue, another part is called high cycle fatigue. That means if failure of any component is occurring till 10 to the power 3 cycle, then it will be known as low cycle fatigue. If it is occurring, if the failure is occurring from 10 to the power 3 cycle till the end point is not known to anyone, so that type of failure is high cycle fatigue. We also discussed about what is stress concentration, and what is this term called KT. KT is your stress concentration factor given by symbol KT, which is given by sigma max, maximum stress, divided by nominal stress. We also discussed about this notch sensitivity term, which is denoted by the symbol Q. We have also discussed what is Kf, that is Kf is your fatigue stress concentration factor, and it is given by Kd is equal to 1 upon Kf, or and this Kf is also given by this equation called 1 plus Q times of Kt minus 1. If the material is having no sensitivity, value of Q will be 0. If value of Q is 0, in this expression Kf will become 1, and when material is fully sensitive to notches, that means in the material only notches are present, more and more notches are present, then in that case value of Q will be equal to 1, and if you substitute Q equal to 1 in this expression, then your Kf becomes equal to Kt. Then we found out the value of endurance limit. We know that endurance limit is given by Ka, Kb, Kc, Kd into Se dash, and this Kd is given by 1 upon Kf, and Kf is given by 1 plus Q times of Kt minus 1. All these things you have to keep in mind for solving problems. Then we discussed the different types of problems which are available in fatigue. Basically, two type of problems are there. First one is when any component is subjected to completely reversed stress, and second, when component is subjected to fluctuating stress. Again, this fluctuating stress component can be divided into two types. If you are designing any problem for infinite life, how to solve that problem, and if you are designing any problem for finite life, then how to solve that problem. All these things we have seen in the last class. So in today's class, we will be discussing about the endurance diagrams, that is Soderberg line, Goodman line, and Gerber line. What is these things? Soderbergh line, Goodman line, and Gerber line. See, likewise, theory of failure. We know that theory of failure is applicable for a mechanical component on which static load is acting. Then I can say that yes, if on any component static load is acting, then that component will fail according to distortion energy theory of failure, principal stress theory of failure, or shear stress theory of failure. But if in any component fluctuating load is acting, that means if that load is changing time to time in that component, then how you can say that which particular theory of failure it will follow? Then the failure of that particular component is given by three particular lines. Those lines are your Goodman line, Gerber line, and Soderbergh line. How these lines are formed? Since we know that Goodman, Gerber, and Soderbergh line will come into picture when the component will be subjected to fluctuating stress. And we have seen that when the component is subjected to fluctuating stress, then it has two components. One component is called the alternating component of the stress. Another component is called the mean component of the stress. And how we find out? Alternating component is half times of sigma max minus sigma mean, and mean component of the stress is given by half times of sigma max plus sigma mean. So if we use this concept over here, so this all these three diagrams, Goodman, Gerber, and Soderbergh diagram, they are plotted along two axes. In x-axis we are having mean stress sigma m, and in y-axis we are having alternating stress or stress amplitude sigma a. Why? Because fluctuating stress is having two components. One is alternating component, another one is mean component. Fine. So if we are talking about only, say, if mean component is present, if mean component is present in any particular if any particular component only mean stress is acting, and if mean stress is acting, that means wait, yes, if you see this diagram, this is my mean stress, this is my mean stress. If in any component if mean stress is acting, that means that component is subjected to static load. That component is subjected to static load. If in any component alternating stress is acting, that means that component is varying with time. You can see the alternating stress is varying over mean stress. Mean stress is your baseline. Over that baseline, your alternating stress is varying in nature. So if I am talking about mean stress, that means static load. That means the load acting on the component is static in nature. So maximum failure point of any component subjected to static load can be what? It can be either SYT, if the material is ductile in nature, yield strength will be the failure criteria, or ultimate strength, that is SUT, will be the failure criteria. But if you talk about only the alternating component, that means if a component is subjected to only alternating stress, that means from this diagram it is very much clear that if any component is subjected to alternating stress, that means that on that component the load which is acting on that component is varying with time. Then only the stress will vary. See, as the time increases, stress is also varying about this mean line. So when alternating component is present, then when alternating component is present, then only your fatigue will come into picture. Because for fatigue you need a load that will vary with time. Then in that case, your body will fail when? Your body will fail in fatigue failure, And in fatigue failure, if your body is failing, I say that body is failing at the endurance limit point. So your AC is the endurance limit point, and SYT, if the material is ductile in nature, then the maximum limit point will be yield point, that is SYT, and this endurance limit is always lesser than that of your yield limit. Fine. Then on this sigma m sigma a plot, if I draw a line, a straight line joining SE in y-axis to SYT in x-axis, that particular line is known as your Soderberg line. If you join a straight line joining AC in y-axis to SUT in x-axis, that means the second line, this line will be your Goodman line, and the third line is nothing but a curved parabolic line joining AC in y-axis to SUT in x-axis. This particular line is known as your Gerber line. So if any particular, that means if any combination of sigma m and sigma a, if it is lying inside these curves, inside Soderberg line, Goodman line, and your Gerber line, then your component is safe to design. But if any combination of sigma m and sigma a is lying outside these points, outside the say Gerber line, then your material will fail completely. But if it is outside Soderberg line, then your material is safe. Your material is safe for Gerber line, but it is unsafe for Soderberg line. But if any point is inside the Soderberg line, say one point is over here, then that particular component for value sigma m and sigma a will be safe for Soderberg line also, Goodman line also, and Gerber line also. Is the step clear? Hello? Hello?
हाँ सर.
Clear है?
हाँ सर.
Okay, okay, fine. So if I want to find out the equation of Gerber line, since it is a parabolic curve line, so it has to follow the equation of parabola, and remaining two lines, Soderberg line and Goodman line, it is a straight line equation, and I know that straight line equation is given by x by a plus y by b is equal to 1. That means wait. Okay. Equation of straight line is x by a plus y by b is equal to 1. What are a and b? A and b are intercepts on x and y axis. So if I want to write down the equation of Soderberg line, for Soderberg line, equation will be x. X is your sigma m, so sigma m divided by a. A is the intercept on x-axis. For Soderberg line, which one is your intercept on x-axis? SYT. So sigma m by SYT plus y. Y is your sigma a. Sigma a divided by b. B is intercept on y-axis for Soderberg line. So this is the Soderberg line. Intercept on y-axis is this SE, because this line is joining AC in y-axis. So by AC is equal to 1. So this is the equation of Soderberg line. Sigma m by SYT plus sigma a by SE is equal to 1. Similarly, if you want to write the equation of Goodman line, it will be y-axis sorry, x-axis sigma m divided by intercept on x-axis, that is SUT, plus y-axis, that is sigma a divided by your intercept on x-axis, that is SE, that will be equal to 1. And for Gerber line, it has to follow the equation of parabola, that is intercept on x-axis, that is sigma m upon SUT whole square plus sigma a by SYT is equal to 1. Now we know that sigma, if I include factor of safety into account, I know that factor of safety is equal to failure stress by allowable stress. I know that factor of safety is equal to failure stress by allowable stress. So if I talk about Soderberg line, if I talk about Soderberg line, fine. Now sigma A by SE, sigma, okay, factor of safety will be failure stress. Failure stress is say SA at any particular, SA means endurance limit of any particular component when amplitude stress is acting. Fine. So your factor of safety becomes failure stress SA by allowable stress sigma A. Sigma A is SA by factor of safety. So in case of sigma A, you can replace it SA by factor of safety. In case of sigma A, in case of sigma A, you can replace it by SA by factor of safety, that is SA by factor of safety divided by SE. Similarly, plus in place of sigma M, you can replace it by this value Sm by factor of safety, and then if you solve and take FOS common, then you will get this expression. That is for Soderberg line, this equation becomes Sm by Syt plus Sa by Se equal to 1. For Goodman line, this equation becomes Sm by Sut plus Sa by Se is equal to 1. And for Gerber line, this equation becomes Sa by Se plus Sm by Sut whole square is equal to 1. So no need to remember all these equations. You just remember this equation, that is this equation for Soderberg line, remaining the two equations for Goodman and Gerber line, and then accordingly you substitute in place of sigma m SA and SE with factor of safety. Is it clear? All these lines are clear? Soderberg line, Goodman line, and Gerber line.
Yes, sir. Yes, sir.
Okay. Next is modified Goodman diagram. What is this modified Goodman diagram? Here in this diagram, you combine. What you combine? You combine the yield line. That means, okay, wait. So I know that my y-axis is sigma A, alternating stress, and my x-axis is sigma M, mean stress. This is my SYT, because if I only consider static load is acting, then if the material is ductile in nature, it will fail at SYT, and if the material is brittle in nature, it will fail at SUT. Similarly, but if I consider alternating stress, in alternating stress, load is changing every time with respect to time. That means fatigue is happening. If fatigue is happening, then according to fatigue, material can fail at endurance limit SE, and material can fail at SYT if I talk about ductile material, and SYT is bigger than that of SE. Now if you join SYT from y-axis to SYT in x-axis, This particular line is known as your yield line. This particular line is known as your yield line. But if you join AC, if you join AC with SUT, that is what? If you join AC with SUT, this is your Goodman line. This is your Goodman line. Fine. Now, modified Goodman diagram is obtained by combining the yield line and the Goodman line. For example, say if you take any point over here, if you take any point over here, where wait, okay. Say my coordinate sigma m is say 40 megapascal and my sigma a say 60 megapascal. That means it is what? It is a coordinate point 40 comma 60, in x 40, in y 60. If this point is somewhat over here, if this point is somewhat over here, then according to Goodman theory of failure, my component will be safe according to, because this is the Goodman line, this is the Goodman line from AC to SYT, and the point is coming inside the Goodman line, material will be safe. But if as well as the material will be safe according to yield line also. Why? Because this is my yield line, this is my yield line, and the point is inside the yield line. But if I place any point over here, say sigma A comes out to be 80 and sigma M comes out to be 80 and sigma A is say 5. Say this is that point. Now if you see this particular point, according to Goodman theory of failure, it is safe. But according to yield theory of failure, this point is coming outside the yield region. So the component is unsafe to design. In order to make it safe, that means whatever point is coming between this region, it will be unsafe to design by yield line, but will be safe to design by Goodman line. So here what I am doing is I am combining both the two lines. That means this much portion I have taken from Goodman line, and this much portion if I take from yield line, that is, see, this much portion if I take from Goodman line, and this much portion if I take from yield line. Now the region becomes O A B C. O to A to B, B to C, C to O. This particular region represents your modified Goodman diagram. This particular region represents your modified Goodman diagram, because see, if in this region you take any particular point, if you take this particular point, according to this theory of failure, Goodman theory of failure, your component is safe to design. According to this much yield theory of failure, point is over here, your component is safe to design. So this is modified Goodman diagram. Is it clear, this modified Goodman diagram? Hello. Is the modified Goodman diagram clear to you? Hello. Hello. Since no one is responding, so I will assume that it is clear. Next, if if in a component which is undergoing fatigue, if on that component combined loading is acting. Combined loading means combination of bending and tensile, or combination of tensile and torsion and so on. Then how to design the component? In that cases, the two-dimensional stress, that is sigma, is given by this expression under root sigma x square minus sigma x into sigma y plus sigma y square. Resultant stress sigma. Fine. And the mean stress sigma m, it is given by under root sigma x mean square minus sigma x mean into sigma y mean plus sigma y mean square. That means mean stress along x direction and mean stress along y direction. And alternating stress is given by sigma alternating is equal to sigma x alternating square minus sigma x alternating into sigma y alternating plus sigma y alternating square. And if bending and torsional moment is occurring in any problem, then how to calculate the value of sigma a and sigma m? Sigma a is given by under root this sigma x a ka square, the sigma x a square plus 3 times of tau x y a square. These equations already you have studied in theories of failure, that if a combined load is acting, how to get the value of sigma and how to get the value of tau. Similarly, sigma m, that is mean stress, is given by under root sigma x m square plus 3 tau x y m square. If you use this equation, then you can find out or you can design the component for combined stresses. Is it clear? Hello? Hello? I hope it is clear. Next, now let us solve some problems that has been asked in previous year's gate. Let us solve problem number 1. A bar is subjected to a combination of a steady load of 60 kilonewton and a load fluctuating between minus 10 kilonewton and 90 kilonewton. Full stop. The corrected endurance limit of the bar is 150 megapascal. Yield strength of the material is 480 megapascal and ultimate strength of the material is 600 megapascal. The bar cross section is square with side A. If factor of safety is equal to 2, then the value of A in mm according to modified Goodman criteria is dash. It has been asked in 2018. So can you tell me what all things are given to me and how we can proceed? By looking at this question, tell me what all things are given to us and how we will proceed for this question. Hello, can you hear me?
Yes, sir.
Okay, so how we will proceed? क्या क्या दिया है इस क्वेश्चन में, पहले ये बताओ मेरे को. क्वेश्चन में क्या बोल रहा है और कैसे सॉल्व करूंगा? क्या बोल रहा है क्वेश्चन में? इन क्वेश्चन इट हैज बीन टोल्ड टू यू दैट अ बार इज सब्जेक्टेड टू अ कॉम्बिनेशन ऑफ स्टेडी लोड। मतलब एक बार है, ठीक है, उस पर्टिकुलर बार पे एक स्टेडी लोड लग रहा है जिसका मैग्नीट्यूड है 60 किलो न्यूटन, फाइन, एंड अ लोड फ्लक्चुएटिंग बिटवीन -10 किलो न्यूटन एंड 90 किलो न्यूटन। उसी पर्टिकुलर बार में फ्लक्चुएटिंग लोड भी एक्ट कर रहा है, दैट इज varying from -10 kilonewton to 90 kilonewton. That means in this problem two type of load is acting on same particular component. First load is static load whose magnitude is 60 kilonewton given to me, and the second type of load is fluctuating load which is fluctuating from -10 to 90 kilonewton. Fine. The corrected endurance limit of the bar is 150 megapascal. That means what is given to me? Endurance limit SE is given to me. That is 150 megapascal. Yield strength of the material is 480 megapascal. That means SYT is given to me, which is 480 megapascal. And ultimate strength of the material is 600 megapascal. That means SUT is given to me as 600 megapascal. The bar cross section is square. That means the cross section of this bar is square whose side is a meter. Now if factor of safety is 2, factor of safety given in the problem is 2, we need to find out the value of a, that is side square a, by modified Goodman criteria. Since I know that modified Goodman criteria is obtained by adding yield line or by combining yield line with the endurance line, yield line with the endurance line or the Goodman line. So before proceeding for the modified Goodman diagram, let us convert the entire load into a fluctuating load. How you will convert? See, static load is 60 kilonewton and fluctuating load is fluctuating from -10 to 90 kilonewton. So minus 10 plus 60, -10 plus 60 is how much? 50 kilonewton. And on this side, how much? So lower limit we have decided, lower limit is 50 kilonewton, and the upper limit of the fluctuating load is how much? 60 kilonewton plus 90 kilonewton, that is 150 kilonewton. So I have divided my entire problem into a one common fluctuating load varying from 50 kilonewton to 150 kilonewton. That means F minimum is 50 kilonewton and F maximum is 150 kilonewton. Now, what I can find out? I can find out the value of amplitude load. How I can find out? Since I know that sigma A is equal to half of sigma max minus sigma min. Similarly, amplitude load Fa will be given by half times of sigma F max minus F min. F max is how much? F max is 150. F mean is how much? F mean is 50. So half times of 150 minus 50, that is, I will get the value of Fa as 50 kilonewton. Is the step clear? कैसे निकला Fa?
Yes, sir.
Okay. Now, if I have calculated the value of Fa, I can get the value of Fm, that is mean load. Mean load is given by half of F max plus F mean. F max is 150, F mean is 50. So half of 150 plus 50. So F mean is 100 kilonewton. F mean is 100 kilonewton. Fine. Now, if I have calculated the value of Fm, if I have calculated the value of Fa, so I can calculate sigma A, that is alternating stress, and sigma M, that is mean stress, sigma A alternating stress, and sigma M, that is mean stress. So sigma M mean stress is how much? Mean load by cross sectional area. Mean load is Fm by cross sectional area of square is A into A, that is A square. But A I need to find out. So the value of sigma m comes out to be 100 into 10 to the power 3 by A square megapascal. Similarly, I can get the value of sigma A, that is alternating stress. It is given by FA, alternating load divided by area. Area is side of the square. It is A into A square. FA also we have calculated. That is 50 kilonewton. That means 50 into 10 to the power 3 divided by A square megapascal. Is it clear? Sigma m and sigma a. क्या कोई डाउट है किसी को?
No, sir.
Okay. Now we have to use what? We have to use modified Goodman theory to solve the problem. We know that modified Goodman theory is the combination of yield line and fatigue line. So let us write down the equation. Let us write down the equation of this Goodman line. That means this which line? This A to F. This A to F line. A B F line. Fine. This is the Goodman line. Its equation will be. I know that in y-axis it is sigma A divided by intercept AC plus x-axis sigma M divided by intercept SUT. So sigma A by AC plus sigma M by SUT, which is equal to 1 by factor of safety. Already I have told you that this SM and SA is given by sigma into FOS. So in I have to substitute in, if you can substitute in place of sigma A, SA by FS or SM by FS. But FSA and SM is not known to you. So better substitute it by sigma A itself. So AC already I know, that is endurance limit stress given in the problem 150, and SUT is what? SUT is ultimate strength of the problem, that is also given to me, that is 600 megapascal. So sigma A by 150 plus sigma M by 600 is equal to 1 by factor of safety. Factor of safety given in the problem is 2. 1 by 2. Fine. Sigma A we have calculated 15 into 10 to the power 3 by A square. 15 into 10 to the power 3 by A square plus sigma M. Sigma M is 100 into 10 to the power 3 by A square. So sigma M is 100 into 10 to the power 3 by this A square, that is 600 into A square, which is equal to 1 by factor of safety, that is half. If you solve this expression, you will get the value of A, that is 31.62 mm. But this is not my answer of side A. Why? Because I have to solve this problem by modified Goodman diagram. If this question they have asked you for Goodman diagram, then A is equal to 31.62 mm, which is nothing but the side of the square is our answer. Since we have to solve it by modified Goodman diagram, and I know that in modified Goodman diagram there are two regions. One is your Goodman region and another one is your yield region. Now I have to write down the equation for yield region. I have to find out the value of side square A, and whichever is maximum, that I will take and I will design it. So let us do it. Yes, equation of yield line. Equation of yield line will be how much? Equation of yield line will be sigma m. This is my line. This DC is my line. Sigma m by intercept, that is SYT, plus sigma a divided by intercept, that is SYT. So sigma m by SYT plus sigma a by SYT equal to 1 upon factor of safety. Sigma m already given in the problem. Sigma a is also given. Fine. Now, if you solve this equation, this yield line equation, you will get A is equal to 24.99 mm. So, out of these two values, that is from this equation, A is equal to 24.99 mm, and from Goodman line equation, A is equal to 31.62 mm. So, what will be the diameter? That is, what will be the bar cross section? area. So the bar cross-sectional area is the biggest of the two values, because if the design is safe for bigger value, automatically it will be safe for smaller value itself. So the correct answer is 31.62 mm. That means this. What is it clear? First question. Any doubt in this question?
No, sir.
Fine. So you have to apply such kind of concepts to solve the problem. The problem is not difficult. यहाँ पे देखो ये प्रॉब्लम डिफिकल्ट नहीं है, सब कुछ फॉर्मूले में ही हो रहा है, बट किस टाइम पे कौन सा फॉर्मूला लगेगा वो थोड़ा आपको ध्यान रखना पड़ेगा. ठीक है. Let us solve next problem, second problem. Fine. Now you will solve this problem
सर
and you will give me
सर
the answer. Hello.
आप बस छोड़ दीजिए सर, 5 मिनट बाकी है.
256.
सर चार्ज भी नहीं है सर.
Acha, okay, okay, fine. So then what I'm doing, I'm stopping it over here, but make sure there is a quiz on this particular fatigue topic. Fine.
ओके
At
सर.
around 4:30 p.m. So I will give the Google form link on your official WhatsApp group at 4:30 p.m. That link will be active till 5 p.m. Fine.
ओके सर.
Okay, fine. Okay, thank you.
थैंक यू सर.
Hmm. Okay, Krishanu, should I continue or should I stop over here?
Sir, let's stop over here.
Acha, okay, okay, fine. So
Okay, I
at
am leaving.
4:30, okay, fine, fine, okay.